Hello everyone, today for a nuts and bolts topic on my channel I want to talk about aircraft engines, and that is piston engines for this video. And I want to talk about the difference between a gasoline piston engine, so an engine that burns 100 low lead or UL91 or MoGas or anything like that, and a diesel engine like the one you would find in a DA42 or in a diesel-equipped DA40 from Diamond, or various Skyhawk and Skylane conversions with aftermarket diesel engines. Diesel engines are not hugely popular in general aviation, so there's not many planes that use them. But the reason I want to talk about them is that it makes it really easy to get into the topic of turboprops. Originally, I wanted to talk about the operation of a piston aircraft engine versus the operation of a turboprop. And when looking deeper into this topic, I found that the turboprop is much easier to understand if you look at the diesel engine first, because as we will see, a turboprop or jet engine, which is at the core of the turboprop, is like a stretched out continuous diesel engine without pistons and using compressors and turbines instead. But the underlying principle, the chemical principle of how the fuel is burned and how chemical energy in the fuel is converted to heat energy and then to mechanical energy, that is very similar in the diesel engine and the turboprop. So follow me along on this comparison of the spark ignition gasoline engine and the compression ignition diesel engine, and next week or in 2 weeks or whenever I get to record the second video, we will look how this segues into turboprops. Alright, let's look at our spark ignition engine with our typical 3 control knobs. We have the black knob, the throttle, which is our primary control of power output. We have the blue knob, the propeller lever, which you can think of as the gearing, the transmission. It is what links the engine to the medium. So in a car, the transmission links the engine via the tires to the road. And in an airplane, the propeller does the same thing. It links the engine to the air that we are moving. And we change the gearing, so to speak, of the propeller with the blue knob, with the propeller lever. And finally, we have the red knob, the mixture lever, which is poorly understood even by many real-life pilots. And of course, a better understanding of the mixture lever in real life leads to much higher fuel economy, lower fuel costs, and in X-Plane it just feels good to do it the right way. On the other hand, with the diesel engine, with the compression ignition engine, we only have one lever, the power lever. Let me make it clear though that having no propeller control, no blue knob, is not inherent to the diesel principle. There's no reason why the diesel-powered Diamonds could not have a manual propeller control. The only reason why they did away with the blue knob is that these engines are FADEC, Full Authority Digital Engine Control, and the FADEC system also controls the propeller. But the principle of the propeller, that it is variable in pitch and that it has a governor that changes the pitch of the propeller blades in order to keep the RPM, that is exactly the same as with a gasoline burning, 100 low lead burning piston engine. So the propeller system is the same, it's just that the input that we give to the propeller governor, instead of having the blue knob operated by the pilot, in case of the Diamond diesel-powered airplanes, this input comes from the FADEC computer instead of the pilot. But there's no inherent reason why we couldn't have a manual blue knob control on a diesel engine. It's merely a design decision. Hey, we have the computer anyway, let's have the computer also figure out the optimum RPM, and that's what they did. But there's no mixture knob, and we'll get into why this is. So you will notice I have referred to the gasoline burning engine as a spark ignition engine and the diesel engine as a compression ignition engine. And that is actually the technical term for what these engines do, how the combustion process in these engines work. And nowadays, we are getting those categories drift towards each other, and there's an overlap in category in modern car engines. So if you have a Mazda Skyactiv or something, they have what is called SCCI, spark controlled compression ignition. So the divide between the spark ignition and the compression ignition engine is weakened in modern car engines, where they actually use compression ignition with gasoline burning engines in some regimes. I am no expert on modern car engines, so everything I tell about engines here is like 70s technology. I'm really only talking about really old school engines. If you are interested in modern car engines, precisely at the line of this divide, like SCCI, spark controlled compression ignition, you are on the wrong channel. Head over to Jason Fenske's Engineering Explained channel. He explains Mazda Skyactiv and other SCCI engines, and he's of course knowledgeable about car engines, and I'm not. So whenever I explain this divide here, keep in mind that your car engine probably works different, and we are really talking about technology from the 70s here. All right, so in order to burn our fuel, the gasoline, we need a certain mixture. We need air, or more precisely oxygen, and the fuel. And the optimum ratio of burning air and fuel in a gasoline-powered engine is 14.7 to 1 by weight. So we need 14.7 kilograms of air, which is a certain volume, because when you multiply it by rho, because air has a density, it's not weightless. So 14.7 kilograms of air and 1 kilogram of fuel. That mixture is what we call lambda equals 1. So lambda is the ratio of air and fuel, and with 1.0 meaning the optimal, or the chemists call it stoichiometric ratio. At this ratio, every molecule of fuel meets a molecule of oxygen. The reaction happens, and we are left over with no leftover oxygen and no leftover fuel if the combustion was really perfect. So looking at this curve here, this is the power output, the amount of energy that we get from burning this fuel-air mixture. And on this graph, the lean mixture, so more air, less fuel, when you pull back on the mixture control, when you pull back on the red knob, is on this side. And the rich side, so more fuel, less air, is on the side where you push in the red mixture knob. And what you will see is that around this optimal 14.7 to 1 mixture, the curve is kind of flat. So as long as you are in the general vicinity of this 14.7 to 1 ratio, the engine runs quite good. If you go over to the rich side, it continues to run fine for some time here. Of course, it gets less efficient because we are burning more fuel. The engine will run cooler because we're not burning all the fuel. The combustion itself will be slower, so this will lead to lower exhaust gas temperatures and lower cylinder head temperatures, which is why we want to run there for takeoff when we're extracting the absolute maximum amount of power from our engine. And you will see, if we go even further to the rich side, at some point the curve begins to fall precipitously and goes down to 0. And this is what happens if you were flying a normally aspirated engine, so an engine that has no turbocharger, and you fly it up into the flight levels as high as it will go, and you never touch the mixture control. Because what happens there is the partial pressure of oxygen gets lower, and with each amount of volume of air we can take in, so piston goes down, sucks in the ambient air, which the given volume, I mean the volume is given by how much the piston moves and the bore of the cylinder. With each volume, we take in less weight of air because the air is less dense. So what happens here? We have an excess amount of fuel because we have not changed the fuel to air ratio in volume, and we have less weight of air. So what happens? We move over to the rich side of the curve, and first we are losing efficiency, and then we are losing power. And that is why it's crucial in normally aspirated aircraft. As you climb into higher altitudes, you need to pull back the mixture control knob. You need to lean out the engine to reduce the amount of fuel going in, to keep the weight of the fuel and the weight of the air in the burnable range. So some continental aircraft engines have what is called an altitude compensating fuel pump. So some Bonanzas, their continental engines have a fuel pump with an aneroid that senses the ambient pressure and lowers the fuel pump output automatically. So there's not much you need to do with the mixture control. Or a turbocharged, or rather turbo normalized, let's talk about turbo normalized to be precise. Turbo normalized engine will keep the intake air pressure high by compressing it with a turbocharger, and this way we keep the air at more or less sea level ambient density. I say more or less because while we can keep the pressure up with the turbocharger, we are also heating up the air while we compress it in the turbocharger, and that heated air is still less dense than the air at sea level that we're taking in at ambient pressure and not grinding it to the turbocharger and compressing it. So that's why it makes sense to have an intercooler or an air-to-air intercooler, which most modern turbo-normalized engines, such as the TIO 550 Continental, have dual turbochargers, dual intercoolers to offset this effect of the air getting too hot. So with a turbo normalized and intercooled engine, we also don't need to tweak the mixture control very much as we climb, because the air pressure stays high. All right, so suppose we are at less than maximum power, and we have set the mixture control optimal for our altitude. What is optimal? Well, that depends on your mission. If you are taking off from, let's say, the Grand Canyon National Park Airport, which has an airport elevation of, I don't know, 8,000 something feet, it's high. At this point, the optimal mixture you want for takeoff is the one that gives you peak power. So you lean out the red knob to give you the absolute maximum power. And that is somewhere on the rich side of the 14.7 to 1. Theoretically, at 14.7 to 1, you would get the absolute maximum power. In practice, the mixture is not perfect in the cylinder, so you cannot really achieve this. Really, each molecule of fuel finds a molecule of oxygen. You need a little bit more fuel so that no fuel goes unburned. So for the takeoff, you're a little bit on the rich side, and in cruise at, let's say, 10,000 feet or so, you pull back the mixture even further. You go across the peak at the 14.7 to 1 at lambda equals 1. This is when your EGT needle, the EGT gauge, peaks and comes back to cooler. Not all engines can do that. The reason is there's a cylinder to cylinder and also a cycle to cycle variation in the combustion, especially with carbureted engines. You need the engine. The mixture is made at one central carburetor, and then the pipes that go, the intake runners that go to the intake ports of the cylinders are not all of equal length. And what happens is that some cylinders run richer than others, and when you try to get all cylinders lean off peak, some cylinders will be very lean, others will be richer, and that causes vibration in the engine, and that's why it's often not possible to achieve this lean of peak mixture in a carbureted engine. With fuel-injected engines and with aircraft engines, we are talking MPI for your car, multi-point injection. So fuel injection in aircraft engines almost always is a multi-point injection. Not to be confused with the direct injection, so the fuel is not injected into the cylinder. With fuel injection in aircraft engines, the fuel is injected at the intake port, MPI, multi-point injection. There's a few aircraft engines that have single point injection, although they call it something else. They call it pressure carburetor. But you don't find these in the general aviation fleet, as far as I'm aware. All right, so for good economy, we want to be a little bit more on the left side of this maximum line, with which lowers the power a little bit, but the drop in fuel flow is bigger than the drop in power, so our efficiency is better. So if we continued to pull the mixture out even from there, you see there's a very sharp drop in the curve on the rich side, and at about 18:1, the engine quits running. It's impossible to burn this lean of a mixture. Now, modern car engines do a lot better with fuel stratified injection. They can have localized pockets of a richer mixture, whereas the whole combustion chamber is much leaner than this local pocket. So with modern direct injection, fuel stratified injection, you can do a lot better than 18:1. But this is technology that is not available to us in our aircraft engine. So for us at around 18:1, the mixture is too lean to burn and the engine just quits. So how do we control the power output of the spark ignition engine? Well, with the throttle. With our black knob, we change the butterfly valve in the intake manifold, allowing more or less air in, and the amount of fuel that matches the amount of air we let in with the throttle valve is matched by either the carburetor, the pressure carburetor, or the fuel control system of the multi-point injection. So primary power control is by how much air we let into the engine, and then we match the fuel to it. So when you run at anything less than full throttle, you're literally throttling the engine. What happens is the piston moves down with the intake valve open. It's trying to suck in the air, but it has to work against the butterfly valve, the partially closed butterfly valve. That creates a vacuum behind the butterfly valve. That's what you see on the manifold pressure gauge. It's less than ambient, it's less than 29.9 when you are at a partial throttle. And of course, this sucking against this resistance of the throttle valve, that lowers the efficiency of the engine. What we call the volumetric efficiency of the engine is less than ideal at anything but full throttle, because we are not sucking as efficiently as we could. So running the piston engine at anything but full throttle is not really efficient, which is why we like to cruise at high altitudes, well, assuming the winds are the same. We like to cruise at altitudes that lower the ambient pressure so much that we can just leave the throttle fully in, the throttle valve fully open, and we get like a 24-inch, 23-inch manifold pressure at full open throttle. And that is the most efficient way we can run our engine, because we have no losses from the throttle valve. We run at full volumetric efficiency, and because we're not anywhere near full power, and we can run the engine at close to the ideal mixture, or even lean of the ideal mixture with very high EGTs without running into CHT limits. If you tried to run the engine at the optimal mixture at sea level with 30 inches of manifold pressure, most engines could not take this very long, because it drives up the cylinder head temperatures. And why does it do that? Let's look at the combustion process. What I've plotted here is the internal cylinder pressure over the crankshaft angle. So what you see here, the piston is coming up for the compression stroke, and at this line here, which is labeled TDC, top dead center, the piston tops out at the highest setting it'll go, and then in the power stroke, of course, the piston moves down again. If there was no combustion at all, the curve would look like the blue curve here. It would just compress the air and decompress the air again. The curve would be symmetrical, no power made, except for friction losses, of course. But this is if the cylinder was just pumping air and no combustion takes place. So, but we are not injecting, we are injecting fuel, so we are not running on air alone. And at about 20 degrees before top dead center, the spark plug fires and ignites the fuel-air mixture. Why do we do this before the piston is at the top? Doesn't that seem to be counterproductive? Well, what happens in the piston is not an instantaneous explosion. When the spark plug fires at 20 degrees before top dead center, it's not like everything blows up all at the same time. No, we get a flame front going in the cylinder that moves out, as you can see here, from the spark plug. It moves away into the pre-mixed fuel-air mixture that is in the cylinder. This flame front takes a while to get going, and until everything in the cylinder is burned, until this flame front has reached the cylinder walls going outward from the spark plug, we are about here in the process. So it takes a considerable amount of crankshaft rotation for this combustion to get going. And in fact, at about 20 degrees after top dead center is when we really want the highest pressure, because at this point the crankshaft is in a place where the piston pushing down actually does something. If we achieve the pressure before that, the piston pushing down merely exerts stress on the bearings in the crankcase. It cannot really move the crank, whereas at about 20-30 degrees after top dead center, the piston can really convert this energy into mechanical energy, turning the crankshaft. So the timing of the spark plug is such that if the combustion process goes orderly, we achieve the peak internal cylinder pressure from the combustion at around about 20 degrees after top dead center, where we want it. Alright, so now what happens if we change the air-fuel ratio in there? Well, remember how I talked about at the optimal best power mixture, the combustion happens fastest. So what will happen if we run at best power mixture is that the this curve with the combustion pressure will rise earlier and higher than it does at a slightly richer mixture. So the curve is both higher and peaks earlier than at the desired 20 degrees after top dead center. So what does that do? It increases the stress on the engine, and we see this in the cockpit with the CHT gauge. If we are running at best power mixture or thereabouts, is about where you will see the highest CHT. That can be fine if we are running at a low, like 65% power setting. Then running there is absolutely fine. But doing this takeoff power is a really, really bad idea. What happens excuse me, if we do this at takeoff power? So you have the flame front expanding away from the spark plug. That raises the pressure in the combustion chamber, of course, because this flame front is very hot and expanding fast, about 60 to 80 feet per second when the combustion process moves normally. At a slightly richer setting, like 100-150 degrees rich of the peak side, which is where we want to be for sea level takeoff, and this is how the full rich setting of our engine is usually set. So when the mixture knob is all the way in, the red knob all the way forward, we are at this mixture for a sea level takeoff that yields this 60 to 80 feet per second flame front movement through the combustion chamber. All right, so if we mess with this and get the flame front to move a lot faster, what can happen is that the rising pressure in the combustion chamber triggers combustion beyond the flame front, somewhere here in the pre-mixed mixture in the cylinder. Remember, the cylinder is filled with a combustible mixture at the optimum air-fuel ratio, and if we have the pressure rise enough, that combustible mixture will ignite and combust, even though it was that particular part of the mixture was not touched by the spark and was not touched by the moving flame front yet. So what we now have is we have those little pockets of more flame fronts expanding, so those little pockets of combustible mixture spontaneously igniting, and we have those several flame fronts going at the same time. And this is what we call detonation. So if this happens, we get those little pockets igniting all on their own before the primary flame front has reached them. And this is when the ICP, the internal cylinder pressure, begins to look something like this. So it rises up, and then we get those uncontrolled explosions, those, well, not explosions, but those uncontrolled ignitions away from the flame front in those pockets. And if you look at test stand data from an engine that can actually measure ICP on a cylinder, that squiggly line, this is exactly what detonation in the cylinder looks like. So, as you can imagine, detonation is not a binary thing. It's not like the engine is either detonating or not. So, those tiny pockets igniting ahead of the flame front, those can be very few and far in between. That's not really harmful. In fact, mild detonation is actually considered beneficial in some situations. For example, mild detonation associated with a very high EGT, just slightly rich of the peak, so maybe 25 to 50 degrees rich of the peak side, which is the region where you are most prone to detonation at full throttle or with a turbocharger or supercharger with a very high pressure to begin with. So mild detonation can actually be beneficial for burning off residue, for burning off deposits from the cylinder. You actually want the engine to be in mild detonation if you just put in a new cylinder and you are breaking the cylinder in, because what it does is it raises the ICP, and when you are breaking in a new cylinder or several new cylinders, you want the high pressure to push down on the top compression ring and move the compression ring outward so that the top compression ring is really pushing against the new cylinder wall, scraping it and breaking in the cylinder. So for a cylinder break-in, we actually want to run in mild detonation. And then, of course, as things get worse, either by jacking up the manifold pressure, if you have a turbo-normalized engine that is not set up properly, that allows the upper deck pressure and by extension the manifold pressure to get too high, or if you have a supercharged engine, you're not operating it correctly, in combination with this destructive, I call it, mixture, you can progress into moderate or heavy detonation, where this where instead of the orderly flame front, you have those pockets of mixture just going off at random in the cylinder, and this is what yields this horrible squiggly line with the very high pressure, and also the very high pressure very close to the top dead center because everything happens so fast. So there's a lot of pressure going on, but the crank angle is still not far enough to do anything useful with it. And that's actually the reason why the best power output is not when the combustion is fastest, but the best power output is actually when the compression is a little bit slower, because then we get the peak closer to the 20 degrees top dead center where we can really get work done. Alright, so we've talked about mild, moderate, and heavy detonation. If you run the engine in heavy detonation, you can develop hot spots in the cylinder, typically part of the spark plug ceramic, or if you have some kind of deposit on the cylinder head in the first place, those can get glowing hot. And what then happens is you have a glowing hot spot in the cylinder, and at some point this glowing hot spot is so powerful, combined with the high compression of the fuel air mixture, is that it ignites before even the spark plug fires. So the flame front, the primary flame front, gets going from this hot this hot glow plug, I call it, before the spark even fires. And then we move the point where the pressure starts to diverge even in front of the 20 degrees top dead center. That means the whole curve moves even closer to the top dead center, and that is really, really destructive. That is a situation that is called pre-ignition, and that can destroy your engine in a matter of minutes. You do not want to go there. So pre-ignition can be caused by faulty spark plugs that cannot conduct the heat away from the spark plug into the cylinder head, or by deposits in the cylinder that get too hot. And usually to trigger pre-ignition, you need to be in detonation first. But there's a very people seem to confuse pre-ignition and detonation often. And the difference is detonation happens after the spark plug fired, and the definition of pre-ignition is it happens before the spark plug even fires. All right, so we've talked about the combustion process in the spark ignited engine. We have talked about EGT. EGT is a measure of what happens at the back end of this curve, how the combustion, the late stage of the combustion process looks. And cylinder head temperature, that tells us something about what happens here in the combustion process. High cylinder head temperature means you are combusting at a time where not much useful work can be transferred to the crankshaft. Alright, now let's look at the compression ignition engine now. And compression ignition should already prime you for what is going on. We are not starting the combustion by a spark plug, but the combustion is merely started by compression alone. And that should ring a bell, because we just talked about detonation. Detonation happens when part of the fuel-air mixture ignites by pressure alone. So you can think of a diesel engine as an engine that constantly, always, and exclusively runs in heavy detonation. And that is why they sound so ugly. Because the compression ignition engine is built to run in detonation. The cylinders are stronger, the pistons are stronger, the cylinder head is much stronger. The engine is built for the additional stress of running in constant detonation, and that's why it sounds so horrible. So the optimal pressure, the optimal ratio, fuel-air ratio for the diesel engine for burning diesel fuel is also around the same. It's at 14.4 to 1 by weight, so not much different from gasoline optimal mixture. But the mixture curve looks a lot different for the diesel engine. And in fact, we never, ever run the diesel engine at 14.4 to 1 at the optimum mixture. Instead, we run it very lean from there. Usually between 25 to 1 at the highest power setting down to a whopping 160 to 1. Remember, the gasoline engine quits, it just dies at 18 to 1. And the diesel engine can be run as lean as about 160 to 1 air to fuel ratio. Of course, at a very low power setting. So if you compare those two curves, you see that the gasoline mixture curve drops off extremely fast on the lean side of the optimal mixture, whereas the diesel mixture curve is a very nice slope, very controllable. If you run rich of about 25 to 1, what starts to happen is you get soot. Your engine is going to produce a lot of smoke. So, how do we control the power output of the compression ignition engine? The compression ignition engine has no butterfly valve, no throttle. All right, car engines, there are car diesel engines that have butterfly valve for EGR purposes. Again, if you're interested in that, head over to Engineering Explained or another car related channel. Airplane engines, diesel engine has no throttle valve. So how do we control the power output? What happens if we advance the power lever? The answer is fuel control. We inject more fuel. For increasing the power output, we move to the right side. So we move up the power slope here on the mixture curve. That causes the power output to increase. Then the engine spins up, the RPM comes up, so we are sucking in more air, so we can inject even more fuel. Then the turbocharger starts to spin up and is compressing even more air into the engine, so we can jack up the fuel even more at 25.1. And this is how we arrive at maximum power, by keeping the fuel ratio at maximum of about 25 to 1, and then ramping up the air input by increasing RPM and increasing turbocharger output. And conversely, if we want to bring back the power, we move to the very lean side of this curve. We move down this slope here, injecting less fuel, getting the mixture very lean. We have less exhaust gas this way. There's less energy in the exhaust gas, so if the turbocharger spools down, we are bringing less air in. And at some point then the RPM drops down and we're getting even less air. So the takeaway point here is that we're always running at 100% volumetric efficiency because there's no throttle plate that we need to suck against. So we're always getting as much air into the cylinders as we can at the given RPM, plus even more with the turbocharger. And that is what makes the engine so efficient, that we always run at the full throttle setting and we can control the power output by mixture ratio alone. So a little bit about this exhaust plume here. If you have a diesel engine that has no electronic control, if you just push down on the accelerator pedal in a very old, like the Mercedes 190D, which is best car, the baby Benz 190D, best car ever made by Mercedes, but that's a different story. So if you push the fuel control all the way in and you are injecting all that fuel into the cylinder and you move beyond this about 25 to 1 ratio, closer to the 14 to 1 ratio, you are going to make a lot of smoke. There's a lot of smoke coming out your exhaust pipe. Then the engine spins up, the RPM comes up. At some point, the turbocharger starts spinning and the turbocharger is injecting more air. And with the more air coming in, you're moving back out of the smoke zone, back north of 25 to 1 ratio, and the smoke stops. This is why you see when you're throttling up a diesel engine, you're not throttling it up, you're fueling it up. That's when you push down on the accelerator in a diesel, you get this brief moment where you're running in the smoke zone until the air intake and the turbocharger, which is influencing the air intake until the air intake has caught up with all the extra fuel you're putting in. And with modern electronically controlled diesels, of course, they have a very precise control not to move into the smoke zone. Here they have mass airflow sensors measuring the precise amount of air going into the cylinders and then not injecting more fuel as to not get into the smoke zone. All right, let's look at what the combustion process looks like. Again, we have the crank angle on the x-axis and the internal cylinder pressure on the y-axis. As the piston comes up, compresses the air, the pressure rises, the temperature rises. At some point before top dead center, fuel injection starts. So the diesel fuel is directly injected into the combustion chamber. So it's not injected at the intake port, it's injected directly into the combustion chamber. That gets the flame going, and the pressure rises, and we end up with peak pressure where we want to be at the 20 degrees beyond top dead center. So so instead of the spark firing at one point, we have this range where fuel injection is injecting the fuel into the cylinder. And the flame that gets going looks something like this. The difference is it's not a flame that goes into a pre-mixed fuel-air mixture, which is what the chemists call a pre-mixed flame. This is what happens on the gasoline side. Instead, what happens here is what the chemists call a diffusion flame. So as the front of injected fuel, of those finely granulated fuel droplets, ideally atomized fuel, as this front of fuel comes into the compressed hot air, the flame front moves exactly with this diffusion of the fuel into the air. So you can think of it as a front of fuel coming into the hot air, and slightly beyond the front of the fuel, the mixture ratio is so that combustion is supported, and you have this flame front be directly behind the fuel front, diffusing into the combustion chamber. So in order to achieve this, we need to run the engine at a very high compression, typically about an 18:1 compression ratio. So the volume of the cylinder at bottom dead center versus at top dead center, the combustion chamber volume is like 18 times bigger when the piston is down here than when it is up here. For comparison with the gasoline engine, we are typically talking in aircraft engines of only an 8.5:1 compression ratio, or even only a 7.5:1 compression ratio with supercharged engines. So in order to achieve this, of course, the engine needs to be stronger, the head needs to be stronger, the head needs to be a lot tighter to achieve this super tiny combustion chamber at top dead center. So we need to run, and the Mercedes 190D actually ran at a whopping 22:1 compression ratio in their diesel engines. So the way to think about the diesel engine on your DA42 in comparison to the Lycoming or Continental gasoline engine on your 172 or 182, the way you can think of it is an engine that constantly runs in detonation, and that you are controlling with the mixture control only. The black knob is always in, the throttle is always fully open, there's no way to close the throttle, and the only power control is with the mixture lever, and while you're doing that, you are running in constant detonation. This is the way to understand the diesel engine for a pilot. Imagine that. And the only reason it works is that the mixture curve is so much longer and so much flatter for the burning diesel fuel than it is for burning gasoline. And that is the only reason why controlling the power by means of a mixture only, this is why it works. So the benefits of this is that the combustion is extremely efficient, both due to the high compression ratio, which also means there is a lot of room for expansion when the combustion happens, because you're increasing the volume in the cylinder 18 times as the combustion is going. So what that means is, by the time this 18-fold expansion has happened, the EGT is extremely low. So what you will find when you fly a DA40 or DA42 with a diesel engine is that the EGT is ridiculously low, like 200 and 300 degrees Celsius, as opposed to 700-800 degrees in a gasoline powered engine. And we also have less problem with cylinder head temperatures, because the diesel engines in airplanes are all liquid cooled. They have a thermostat, so we can control the temperature of the engine very precisely. All right, and now that you have understood the diesel engine on an airplane, you're optimally prepared to understand the, what you could call, continuously burning diesel engine, that is the turboprop or the jet engine, which we will get into for another video.